Ever wonder how a rocket gets its push? In our experiment, we are showing how impulse affects the thrust and flight of our rocket. To do this, we will be varying the cross-sectional area and pressure of our rocket launcher, which will affect the impulse and thus the distance our rocket travels.
And now let's see some real-life applications.
This example of mortar fire demonstrates impulse. The impulse force is the expansion of hot gases from the explosive material, which propels the mortar into flight. This impulse changes the momentum of the mortar from falling down the tube to upwards and out of it.
Let's see my...
This cannon also demonstrates impulse. Again, the impulse force is the expanding hot gases inside the cannon, which change the momentum of the cannonball from a stationary position into horizontal flight.
And now time for the experiment.
In our experiment, we varied the cross-sectional area and pressure of our rocket launcher. The cross-sectional area is the area of the opening at the nozzle of the launcher, and the pressure increases as we pump more air into the tank of the launcher. We tested the rocket at cross-sectional areas of 100%, 75%, and 50% of the total area of the nozzle. These are also noted as 0% choke, 25% choke, and 50% choke, respectively. We tested all three area settings at pressures of 40 psi, 60 psi, and 80 psi. The launch angle of the rocket remained constant at 45 degrees. We then measured the distance the rocket traveled after each trial. In our experiment, the impulse force is delivered by the expanding gas from the tank of the launcher. This impulse force changes the momentum of the rocket from a stationary position into parabolic flight. Here are a few trials from our experiment.
0 choke, 40 psi.
Ready? Fire.
Attached to the end of the launcher nozzle is a washer. This washer is used to restrict the cross-sectional area to 75% of the full area of the nozzle.
Okay, we have 40 psi with 25% choke.
Ready? Fire.
That is a lot farther.
This is the washer we use to restrict the cross-sectional area to 50% of full area.
This is 50% choke at 40 psi.
Ready? Fire.
60 psi, 0 choke.
Fire.
$60 psi, 25% choke.
Ready? Fire.
Time to crunch some numbers.
At the top of the page, you will see the equation for mass flow rate. In our experiment, everything under the radical and c at the front of the equation are considered to be constant. We are, however, varying a, the cross-sectional area of the tube's point of discharge. The original diameter of the discharge point is 1.5 centimeters. At this point, there is 0% choke. To achieve 25% choke, a washer with diameter of 1.125 centimeters will be attached. This provides 25% choke. To achieve 50% choke, a washer of 0.75 centimeters is attached to the end of the tube. As you can see, the units for mass flow rate are kilogram per second. This will be essential in connecting our experiment to impulse. We will now analyze the effect of constricting airflow when pressure is a constant 40 psi and the constriction changes from 0 to 45% choke. At the top of the page, you will see the equation for impulse set equal to mass flow rate times the distance of the tube. For both impulse and mass flow rate times distance, the units are kilogram meters per second or Newton seconds. It is very important to note that impulse and m is acting on the rocket as long as the rocket remains on the tube. The resulting parabolic launch of the rocket is evidence of the conservation of momentum. To find the force and the time of this impulse, we must first analyze the parabolic path of the rocket. By doing this, we see the initial velocity of the rocket leaving the tube is equal to the final velocity of the rocket on the tube. We then divided the distance the force is acting by the average velocity of the rocket on the tube. This gives us the time the force is acting on the rocket. By finding the acceleration, we are able to find the magnitude of the force acting. These numbers are then used to find the mass flow rate, which is 2.09 kilograms seconds under 0% choke and 40 psi. By using the same process, we were able to find that when the flow was constricted by 25%, m equaled 3.12 kilograms per second. In addition to increases in the value for m, we saw large increases in the magnitude of the acceleration, velocity, distance, and time the rocket was in the air. We saw a large decrease in the time the rocket remained on the tube as well.
Conclusion.
As you can see by our data, as we increasingly restricted the cross-sectional area of our rocket launcher, both the distance the rocket traveled and the time it was in the air increased. In some cases, further restricting the area did not produce increased distance or time, at which point the cross-sectional area became optimized. Increasing the air pressure of the rocket launcher also increased the flight time and distance, because the increased pressure creates an increased impulse force, and thus a greater launch speed. We suspect our rocket traveled further under area restriction because of Bernoulli's principle. In our experiment, Bernoulli's principle tells us the total amount of air moving out of the rocket launcher over a certain period of time must remain constant, no matter how we restrict the discharge area. For the same amount of air to move through each time, and thus for conservation of momentum to be true, the air must move increasingly faster the more we restrict the area of discharge. We suspect the increased speed of the air when discharge area was restricted increased the force of impulse on our rocket, and thus increased the distance it traveled.